Hello, good morning. This is presentation on the effect of propagation distance on angles of arrival and departure for indoor propagation. The presenters are ANIOKE, Chidera, Linda, and Professor C.I. Ani. The background of the study, we're looking at the indoor environment. The indoor environment is basically an environment that looks like an office building, an airport, a laboratory, a factory, a classroom, etc. They are characterized by uh, its dynamic nature, and this dynamic nature results from the scatterers or objects within the channel and human traffic. Indoor environments are also characterized by spatial and temporal variations of the received signal power. Data rates within the indoor environments are usually limited because of the multiple versions of the transmitted signal going to the receiving side. Uh, One thing that characterizes the indoor environment is wireless connectivity. It's becoming increasingly more practical in the indoor environment because most people spend approximately 90% of their day indoors. If they are not at the office, they are at home. And the flexibility and adaptability, ease of movement, and the technological improvements in communication networks. This figure 1, shows a typical indoor environment. The transmission from the transmitter to the user equipment or the receiver usually follows through multiple signal paths, which we call multipath, to get to the receiver. And while going through multiple paths, uh, they tend to be obstructed by different scatterers within the environment. Aim and objectives. The aim of this research is to measure and analyze the effect of propagation distance on the spatial characteristics of the indoor channel. The specific objectives include determining the best channel model that will be suited for specific propagation distances. Secondly, to exploit the spatial dimension of the indoor channel so as to improve spatial diversity. The third is to achieve better clustering of the multipath components to give us better visibility. Why do we need this research? The indoor environment is complex, like has earlier been stated, and is affected by multiple reflections, diffractions, scattering due to the heavy clutter within the environment. There is usually increase in data traffic because, like I said, most people spend about 90% of their time indoors, and people using emerging and new wireless networks are also increasing from time to time. Due to its flexibility, there is increase in the volume of users in the mobile communication systems. And as a result, we experience multipath fading and interference. There is also a high demand for improved capacity, high data rate transmission, better coverage, no matter the distance applied. Finally, we have a need for boundary requirements as wireless technologies are increasing, and then also we have demand for boldly innovative technologies. Our methodology for improving spatial diversity in indoor channels. Our methodology will focus on employing the two important spatial channel parameters, which are the angle of arrivals and the angle of departure, and comparing them against varying propagation distances. To get the angle of arrival and angle of departure, we need to employ geometrical models, and these geometrical models will be developed based on the fundamental laws of propagation as well as geometry. These geometrical models will also be supported by statistics and measurements. And geometrical models are usually physical models, so they are likely the best bet. Examples of geometrical models in literature are the one-ring model, the two-ring model, the elliptical model, the cylindrical model, and hybrids of either one or two or if two or more of other models. The geometrical models for consideration in this work are the new geometrical statistical scatterer channel model, which will be developed by this work, and the existing geometrical based single bounce model. This is a physical representation of the geometrical statistical scatterer channel model, which is the GSSCM. Here we have two ellipses which are overlapping, ellipse A and ellipse B. For ellipse A, we have the transmitter and the receiver, as you can see T and R, at the foci of ellipse A. Meanwhile, on ellipse B, we have only the receiver at the center of ellipse B. Now, the reason for this is that the circumference or the area surrounding the ellipse is characterized by scatterers. Now, the reason for this pictorial representation or this physical model is because for some scatterers affect both the transmitter and the receiver at the same time. Meanwhile, there are other scatterers on ground that affects only the receivers. And then the major and minor axes are represented by A and B. Then we have R1, which is the distance from the transmitter to scatterer point S, and we have R2, which is the distance from S, the scatterer point, to the receiver. Now, these are steps to determine the PDF of the angle of arrival or angle of departure for the GSSCM. To determine the angle of arrival, the PDF of the angle of arrival, we are going to follow steps 1, 2, 3, 4 up to step 7. And first of all, like earlier stated, we have designed our physical model, and then we'll determine the CDF of the area of the elliptical sector for A, the area of the elliptical sector for B. And to determine that, first of all, we're going to determine the full polar form of ellipse A and ellipse B. And since there are two disjoint events, we are going to add them up. And then from there, we can differentiate the CDF in respect to the angle of arrival to determine the angle of the PDF of the angle of arrival. And then for the angle of departure, in this case, we'll see the transmitter as the center of the ellipse. And so the polar form will be determined relative to the center of the ellipse. Thereby, we employ the same steps we followed in step 1 to 7 to determine the angle of departure. Okay, this is a figure 3, gives us a pictorial how to determine the area of the elliptical sector swept by theta, where R is the radius of the elliptical sector. It gives us a pictorial view of how to determine the polar form of the ellipse. Now, this equation 1, since we are determining most of the signals we are assuming that most of the signals are emanating from the transmitting side of the communication link, the T will be seen as the origin of the ellipse, while R is the positive real axis, where D is the TR separation, and then the polar form relative to the focus will be established as given in equation 1, whereas the polar form of ellipse B, like earlier stated, will be from the center of the ellipse and expressed as given in equation 2. Like earlier stated, we are going to add up the area of the elliptical sector for all scattering points. Since they are disjoint events, we add them up and then we integrate, then find the CDF, and then finally the PDF, which will be determined by differentiating the CDF with respect to theta, or we can apply a technique called the inverse CDF simulation technique. Now, this figure 4 shows the existing geometrical based single bounce model. This model was derived by J.C. Liberty and T.S. Rappaport in 1996. Up to date, variants of these models have been researched or given out in literature. Why we go back to this model as far back as 1996 is to start from the original and see what is obtainable from those variants. Then characteristics of the GBSB. From the GBSB, the assumptions made is that all scatterers should lie in the same plane as the transmitter and the receiver, and this plane is roughly parallel with the ground. Secondly, scatterers are uniformly distributed in this plane. Thirdly, only the azimuth angle is used to characterize the AOA. Normally, we use azimuth and elevation, but since my physical model is showing overlapping ellipses, there was no need for the elevation part, so we only use the azimuth angle to characterize the AOA. The single bounce multipath is the dominant mode of propagation in GBSB, and then it's assumed that a line of sight path exists between the transmitter and the receiver. Then for spatial channel parameters of the GBSB, we are determined by as given in equation 7 for the PDF of the AOA, and then from the AOA we can determine the PDF of the AOD as given in equation 8. This is a table showing the comparison for the GSSCM and the GBSB models after simulation, and graphically the result is shown in figures 5 and 6. And for result analysis, for the first result analysis, we can see that for both GSSCM and GBSB, fewer multipath components were collected by the receiver as the TR separation is increased. That is evident from the table 1. And this can be due to the fact that electromagnetic waves attenuate more after so many reflections from scatterers within the transmission path. That is as presented in table 1. Then secondly, there is a higher spatial multiplexing gain at lower TR separation or propagation distances in a directional channel with the collection of more multiple components around the line of sight point. The line of sight point is usually the 0 degrees point, or the point at which the angle of arrival is 0. Now we have a graphical figure 5 which shows the compared results for the PDF of AOA for both GSSCM and GBSB. Now this is a graph resulting from simulations done, and we can see the GSSCM is the red line while the GBSB is the blue broken lines. And then we can see that from distances of about 1 to 500, the GSSCM seemed much better in application for indoor propagation than from 500 meters up onto 1000 meters. And for also AOD, which is the angle of departure, we see that the same thing is obtainable between the GSSCM and GBSB. Therefore, we can say that for a given angular PDF, which is the AOA, the received signal power is proportional to the gain of the transmitter or the receiver. That's gotten from the Friis transmission equation. This comparison could also be used as a measure for receiver sensitivity. Note that sensitivity depends on the propagation distance. The figures 5 and 6 show improved signal reception for GSSCM propagation distances of for propagation distances of 0 to 500 meters, earlier stated. The new model is therefore the best model for an indoor scenario, which is definitely within the range of 0 to 500 meters. In conclusion, the spatial parameters of the new GSSCM were compared with those of the GBSB model for varying indoor propagation distances. The effect of the different distances on the spatial statistics gave more insight into the dynamic nature of the indoor environment. The GSSCM has been shown to give improved clustering of multiple components, and this gave better visibility. This GSSCM is therefore the best model for improved spatial diversity.